In this video, I want to apply Newton's method a little more systematically. I want to start with 100 possible starting values between -2 and 2. For each starting value, I want to apply Newton's method 7 times, and the result I'll call Z7, and I want to ask, is Z7 almost a root? Okay, where that has this precise meaning here in this case. So let's go ahead and try that out, starting with the exact same setup as in the previous videos. And let's define Z to be this linspace. So np.linspace -2 to 100. And I'm going to hold the results. I think of this as 100 experiments. I'm going to hold the results of those experiments in a NumPy array. So let's call it ARR. And that'll be np.zeros. Make sure to have two sets of parentheses in here and number of rows. I'm going to think of each row as corresponding to a starting value. Okay, so I could write 100 here, but I think it's a little more robust to write length of z. And for the number of columns, I want the starting value and then one column for each application of Newton's method. So let's define another variable here, reps. I'll set equal to 7, and then this will be reps plus 1 for the starting value, and then the 7 applications of Newton's method. Then I think of each row as corresponding to one starting value. So let's put these starting values into the leftmost column, into the 0th column. So ARR colon comma 0. Okay, the colon is like saying get me every row 0th column, and we'll set that equal to z. And let's go ahead and fill in the Newton values at the same time. We'll do that using a for loop. So for I in range reps, and this is really similar to what we did before, except instead of having a one-dimensional NumPy array, here we have a two-dimensional NumPy array. But as far as the application of Newton's method, I get to apply this newt function that I wrote here. I get to apply it to an entire column all at once. That's a nice thing about using NumPy here. We're going to say the I plus first column. Okay, in the previous videos, this was like the I plus first entry instead of the I plus first column. And that is newt of the ith column. Okay, good. Let's just take a look at I. And so what this is doing is this is our first starting point, and then this is where it winds up after applying Newton's method to -2. On the other hand, this is where it winds up after applying Newton's method to -1.9. Okay, great. So next, let's start our analysis. Let's call it, how about results? And that will be the last column of ARR. And so what would you put here to get the last column? I think the best thing to put is -1. Another thing we could put would be 7, since there are 8 columns. Okay, and now let's try visualizing, like, where did this work well? So let's say fig x equals plt.subplots. And let's get some x values to use. This will be np.linspace. Let's go a little further in each direction. Let's go -2.5 to 2.5 and 1000. Okay, this is just for the plotting. Then we're going to do x.plot. And first I'm going to plot the polynomial f of x. Okay, this polynomial here that I've defined with the name f. So that's easy enough. X, f of x. And then this is maybe the more advanced part. What I want to do is I want to draw, let's just look at this to start. And so for 100 starting values between -2 and 2, I want to look for each of those starting values. Did I wind up at a good point in this result? So how can I do that? Well, let's say about good bool, because this is going to be a Boolean array. And what was the condition that I chose? Yeah, I mean, there are a million conditions, but what I chose was the result is close to being a root if when I apply f to it, the absolute value is less than 0.001. Okay, so I want to have the absolute value. I do np.abs, and then I want to get f of results. Okay, these results are where we wound up. So for example, this value here, this rightmost element in some row, this is one entry in our results. So I want to know, is the absolute value of this, is that less than or equal to 0.001? And if I look at this good bool, so this is a Boolean array of trues and falses, where it's true, so like it's starting out with starting value -2. And here it's saying that Newton's array worked well in this particular sense, got close to a root after applying Newton's method 7 times. On the other hand, one of these is probably right in the middle, like 0, and it's saying Newton's method did not work well for that starting value. If you start here and apply Newton's method 7 times, you do not get close to a root. So let me copy this. And what I want to do is I want to draw in bullet points everywhere that it works well. So let's just call this points. And this is going to be D. Remember, that was our original linspace, brackets, good bool. So this is saying keep only those elements, those starting values, where the final result was close to a root. And let's just check what the shape is of points. So it's a one-dimensional NumPy array with length 32. That's like saying 32 of the points worked well, 68 of the points did not work well by this measure. And let's go ahead and plot them in now. ax.plot, and then we'll do points. So these are the x coordinates. The y coordinates are always 0, and let's use black circles for the markers. And let me put a semicolon here just to stop having this kind of output displayed. And so what did I do wrong? This is telling me that the error is in this very last line. And what is the error? It says x and y must have the same first dimension, but they have shapes 32 and 1. So it's saying this has length 32, this has length 1. So how can I fix that? I should use np.zeros instead of 0. Let's use np.zeros length of point. And what did I do wrong? One too few parentheses. Okay, and let's make these bullet points a little smaller. You can do that using marker size. And I tried this out before. 2 seemed to work pretty well. Okay, and before we talk about this, let's go ahead and see the complement of this. What are the bad points? And so how can I get the bad points? Well, I'm just going to negate this good bool. So remember, good bool looked like this. And if I negate it, so that's a NumPy array. Maybe I'll keep these separate so we can see both of them. If I negate it, I use this tilde symbol. So where this one started out with a bunch of trues, this one starts out with a bunch of falses. And so in this case, if I change good bool to the negation of good bool, these are going to be the points where Newton's method does not work well. And let's change the color to red. So these are the points where it did not work well. And let me go ahead and copy this. We can look at both of them next to each other. So you can see that all of these values here between like -2 and -1, all of those Newton's method worked well for. And that sort of makes sense because if you think about the tangent lines here, the tangent lines are all kind of moving in the direction of the actual root. Whereas once I get past this local maximum here, then the tangent lines start moving us away from the root. Okay, and when we look at where does the tangent line intersect the x-axis, we wind up over here, maybe at a worse point. We've gotten further away from the actual root. And if we chose more repetitions, more than 7, we would get a lot more good points in here. But here it's like all good to start, then almost all bad. There are just these couple random values where it also works well. And why do you think these work well? Well, imagine this one here and drawing the tangent line. Probably that tangent line, or maybe this is sort of hard for me to guess, but here if we draw the tangent line, assuming it has a positive slope, then hopefully where that tangent line, like a positive but very small slope, then where that tangent line hits is hopefully somewhere over here in the good region. And so why would this one work better? Well, imagine drawing the tangent line there. That gets us to one of these points after one iteration of Newton's method, and then the next iteration of Newton's method hopefully gets us over here. And why would this be a good value? Well, hopefully we're starting here, then maybe we reach this point, then maybe we reach this point, then maybe we reach one of our good points. Hey, our good point might also be further over here to the left. Those should also work fine. So I hope seeing this visualization, I hope that helps you have better intuition for where Newton's method might work well for this cubic versus where it works less well. And you can see that there's a little bit of randomness to it in terms of there are these outlier points where it's like right in the middle of a bunch of bad points. But for these, Newton's method also works well for this particular cubic.